Good morning and welcome to the Land Grant Seminar Series 2025 Spring Semester. Pleasure today to welcome another speaker, Dr. Tefera. He is a research specialist working on sustainable agriculture drought analysis, hydroclimatic extremes, and optimal water management strategies under uncertainty. He has frequently used in-situ measurements, machine learning, hydrological modeling, GIS and remote sensing, and integrated decision analysis techniques to address some of the most pressing environmental and agriculture challenges in our time. His research contributions are well recognized, resulting in numerous peer-reviewed publications and made over 780 citations on Google Scholar. He is actively writing project proposals, securing external funding, collaborating with other colleagues, and working with graduate and undergraduate students to cultivate the next generation of scholars. Additionally, Dr. Tefera has been a panel reviewer for NASA project proposals through multiple solicitation rounds. With that, I would like to welcome him. Dr. Tefera is going to talk to us about applications of data-driven approaches to study environmental changes and ecosystem fluxes in Texas. Dr. Tefera, the floor is yours. Thank you.
Okay, thank you. Okay, good morning all. Thank you for coming to hear my presentation. And thank you, Dr. Ali Faris, for your warm introduction. Today I'm here to present my research experience in the last few years, and I give a title, Application of Data-Driven Approach to Study Environmental Change and Ecosystem Flux in Texas. Here is the outline of my presentation. I will have introduction about myself, research and educational background of myself. I will have a few slides about climate change in Texas and about soil moisture and carbon flux in Texas, mainly driven using remote sensing products. And I will have more about ecosystem flux and more research, in-situ measurement, more experiment data we have generated from our research farm, Prairie Research Farm, Prairie and University Research Farm. Carbon flux and soil moisture estimation using machine learning, and I will have a summary. So here is my educational background. Originally, I'm from Ethiopia, and my education is mostly from Ethiopia. My first degree was on Geography and Environmental Studies in 2009. And my master's degree was on Natural Resource Management, Sustainable Natural Resource Management in 2011 from Ethiopia as well, from southern part of Ethiopia. And I have another good opportunity to attend another advanced course from Netherlands, the Delft in 2016. Then it was another opportunity to attend the GIS for Geoscientists from India, Hyderabad in 2018. And 2020, I graduated, I completed my PhD, focusing on climate change and water. These are my work experience. First, I get employed as a lecturer at Debre Taw University, Ethiopia. And I have worked there for 3 years and also working as head department of natural resource management. And for about 1 year from 2017 to 2018, I have worked as a research consultant at a Water Land Resource Center of Ethiopia. And it was a good opportunity to work for about 5 months in Water World Bank, an independent evaluation group. And after my graduation from PhD, I have worked for 1 year as assistant professor in Debrtown University, Ethiopia, and I'm here since November 2021, first as postdoctoral researcher in hydroclimatology, and I'm working as a research specialist since April 2024. Here are a broad category about my research areas: climate change and water management, hydrology, and hydroclimatic extremes analysis, GIS and remote sensing, and using this GIS and remote sensing as a data and as a means of analysis, and ecosystem analysis, ecosystem flux, and change in ecosystem is another research area I have. And here, I'm not going to convince you about climate change in Texas. Rather, I'm going to say how the data are saying about climate change in Texas. So I try to start from the instrumental period, instrumental observation, when since then, what is happening? One is the change in temperature. Consistent increase in temperature was observed over the last 2 centuries. But when we see precipitation, it is highly variable, mainly due to different climate regions which drive the precipitation of the region, like Gulf of Mexico, the Eastern Pacific, the Arctic region. These all drive even the natural ecosystems. These all drive high variability of precipitation in Texas. When you see drought, even if we go back this instrumental period, if we consider Holocene period, 0 mega droughts were reported. However, if we see the last 1 or 2 centuries, the drought, 6-year drought in 1950s was the most drought in the history of the state. Here, I try to add these maps just to see how the temperature was over the last 7 or 6 decades, so that you can see the temperature was somehow, temperature is getting more warmer and warmer than 1960s than that of the last decade. And here I try to add some cities, like including Prairie View, and what is happening. Consistent, a linear trend. Of course, there is an increase, a decrease in year, but the trend is increasing in all cities. Particularly, Houston is characterized by high temperature, while Dallas, even though it is low in temperature, the trend is increasing. But what matters most is the extremes, so that I try to see how the frequency of temperature extremes, for example, frequency of warm days throughout Texas. It is the state average, so that if we consider local studies at local scale or at station scale, this trend may be more sharp than that of this one. So if we see the frequency of warm days, these are increasing. For example, the percentage of warm days in 80s or 60s is about like less than 10% of days are warm days, while these are getting increased. And inversely, the frequency of cool nights, these are getting decreased, which means more days are becoming, or more nights are becoming hot and hot. So here I try to see how the frequency of temperature events with 100 or more than 100 degrees Fahrenheit. Actually, this temperature threshold considered as heat waves. So these are events or frequency of hours where temperature was greater than 100 degrees Fahrenheit. If we see Houston, there are some events. Of course, the events are more common in Dallas than other cities. And if we see from the 1940s and the last few decades, these events are increasing year to year. So the only thing what's left is if these events are stayed for 1 or 2 or 3 days, that means heat waves is happening. Rather, these are hours, how many hours in a year where temperature was exceed 100 degrees Fahrenheit. Even though Houston is high in temperature, frequency of this event is less in Houston, while Dallas is low in mean annual temperature. However, the frequency of heat wave or 100-degree Fahrenheit events are higher in Dallas than other cities. We have some localized studies, focused studies, for example, in Central Texas, and to see how the climate change. First, we try to see our climate model simulation. So we start from emission scenarios, how many we consider, global climate models, and we need to downscale. So statistical bias correlation downscaling techniques were applied. After that, we try to see how the precipitation projection and how temperature projection is. And first thing is, we have seen that when we project precipitation, it is high uncertainty, high deviation is among global climate models. While when we project temperature, it is a deviation or uncertainty is higher among emission scenarios rather than climate models. And you can see the emission scenarios, RSP represent a representative concentration pathway, 8.5. Under that, there is high increase of temperature. Actually, maximum temperature is projected under this representative concentration pathway, high emission scenario, which means, while under low emission scenario, which is RSP 2.6, there is consistent or no significant change from the historical period. Again, we try to see the extremes, how the frequency of the temperature and precipitation extremes, even though we have seen a reduction in precipitation. Of course, in some events, some precipitation extremes will increase. And we have also tried to see how the frequency of temperature at Central Texas until the end of this century. So, for example, what to happen on the frequency of these cool nights and cool days here on this one? These are getting decreased, which means more nights are becoming warmer, which is we have seen in historical period for the entire Texas. And we try to see the hydrology, particularly the low flow and high flow, particularly the low flow, which are very important, like for domestic water supply, for agriculture, soil moisture, and of course for some natural aquatic systems, so that we have seen more reduction will be on the low flows rather than high flows. Even in some cases, there will be an increase in high flows under this representative concentration pathway 8.5, even though this scenario is characterized by high temperature, but there will be events characterized by high flows, while still there is significant change will be happen on the low flows, so that there will be a lot of multifarious impacts on agriculture, domestic water supply, particularly on soil moisture. So another thing we have seen in the last few years is about water quality and what to happen on our aquatic, surface water sources. Here is a Waco Dam, which supply water over 200,000 population. So that what to happen if there is a change on the water quality on upstream part of the watershed. So the main thing we have seen is there will be a decrease in total organic nitrogen and organic phosphorus. But the most impressive thing is the concentration of nitrate. Here is the nitrate concentration in the historical period, while our future climate scenarios show there will be more concentration of nitrate in these streams, which are main tributary, more than 80% of tributary for this dam. So that this will have a lot of impact on human health and the health of aquatic systems surrounding this dam. And so we have seen on hydrology, we have seen on water quality. Another thing we have seen in the last years is about change in plant hardness zone. What to happen about the plant hardness zone? Is it suitable? Is it similar in the future? or is it going to be warmer or becoming cold? So we have seen it is in the historical period. This is a plant hardness zone based on the climate from 1981 to 2005. So that what will happen, for example, in this zone, more warm plant hardness zone are becoming wider and wider, increase an area and moving toward the northern part, especially the northern part of this region, Texas and other southeastern states. The northern part is characterized by colder, relatively colder plant hardness zones, while the southern part, these are warm plant hardness zones, so that you cannot plant one tree here and all the states. And it will have a lot to say about mainly the perennial crops, the fruit trees, vegetables like that. So we may need to move our growers, or our growers may have a different decision in the future about growing crops, perennial crops here or in other states. Similar here, we have tried to see how the area of the area under different plant hardness zones, the area under this zone, for example, before I move that, what is, for example, what I say, plant hardness zone 6A. 6A is a region which is temperature, extreme minimum temperature, that is. Extreme minimum temperature happening in these states is in January. So that this plant hardness zone is developed based on the extreme minimum temperature, which is happening in January. So this is not the mean annual temperature. It is the extreme minimum temperature. So the extreme minimum temperature, for example, in 6A is -23 to 17 degrees centigrade. And we don't have these other plant hardness zones in these states and in Texas. For example, monthly our plant hardness zone in this region is ranging from 6A to 12B. There are other areas in the United States where the plant hardness zone exceed 12B, which means 12.8 to 15.6 degrees centigrade. And this is not a classification. It's a classification developed by USDA, and USDA has used this plant hardness zone classification in recent plant hardness zone mapping into 2023. First plant hardness zone was developed by USDA in 1960, and it was revised in 1990. Like mainly, they increased the density of stations used to develop plant hardness zone. And recently in 2023, again, plant hardness zone was revised and developed by USDA. So we have seen the area a significant decrease, like about 10 to 15% decrease in area or under plant hardness zone of 8B, while there will be an increase in area of warm plant hardness zones. So this is not only global climate models or climate models and climate stations we have used to know more about the environmental changes in Texas and the seasonal and spatial changes in Texas. What we use is another set is remote sensing products. Here we use SMAP satellite and MODIS satellites to know more about the seasonal change in soil moisture and carbon flux and vegetation as well. So here, one thing we can say is there is inverse relation between soil moisture and carbon flux. I don't know whether this will happen or this is true in other regions of the world or not. But here, if, for example, if we see high soil temperature in this region, in the cold seasons, January to this spring season, while these seasons are low or emission of carbon to the atmosphere. More sink of carbon in the atmosphere is in these months, May, June, July. However, low soil moisture is observed in these months. So that it's not true, always not to say high soil moisture is going to bring high vegetation cover, then high sink of carbon. that is not true for at least for the case of Texas. And we are now increasing our understanding about the vegetation change, carbon flux, soil moisture. Here, another level is about leaf area index. How is a seasonal change and spatial change in leaf area index throughout Texas? So here, more leaf area index is in these months, and low or no leaf area index is in the western part of the state. This is this area, this eastern part of the state, high in soil and the precipitation that trigger more vegetation cover. However, there is more seasonality, like in these months, you can see there is low leaf area index. So just it is not about knowing or mapping about leaf area index throughout the state. It's about we are preparing ourselves for using these data sets for our ecosystem models, about our for our machine learning techniques. And here I try to extract only the grid which intersect our research farm. And here is a seasonal change in leaf area index, which is exactly only true for our grid, a grid which intersect our research farm. And here we can see low leaf area index in cold seasons like December to maybe until the start of March. So here is our research farm, third part of my presentation. Here is our world, which decide a lot about us, which has a lot of impact, like scientists like me, because this is an area where we want to realize our objectives. And this area where we want to start to reach to our farmers. So first we have to start and we have to make sure about our experiments, about the impact of our experiments on, for example, on ecosystems, on agriculture, water quality, like that. So that this is a lot to say about this one. So it's a big opportunity for me to work on this research farm. A lot of instruments here, but let me show. For example, the first thing is we have more dense equivariance flux stars. There are more than, we have 9 equivariance flux stars with this area. Partly, some of them are installed on croplands, crop agrosystem. Some are installed on pasture agroecosystem. And these are not only equivariance flux stars. We have also soil moisture sensors installed on different agrosystems, different treatments. For example, this is only true only for 2023. Like the number of sensors at that time were not more than 200. But last time we have more than 200 soil sensors were installed. This season we are going to have more number of experiments, more number of projects are going to be started, so that we are going to have more than 5,000 soil moisture sensors, so that you can see how the density of our sensors, and you can estimate or you can understand how the quality of soil sensors are, soil quality, soil moisture, soil temperature, and soil salinity data. And not only the soil moisture sensor, equivariance, we have also these multiplexers, which connect different chambers and automatically measure soil carbon. And we have other stations like GPM, NASA GPM. One is located here, another is located some like maybe 200 feet away from the main greenhouse area. Another is far like maybe 2 miles away from here on 90-acre farm. So we have 3 NASA GPM rain gauges. So today I am mainly focused on equivariance flux stars and soil moisture sensors. Here are the first thing when we say about the equivariance flux star is the EDs, which means the winds. These are the winds. First, we need to be clear about. So when we see the the wind direction, there is more similarity about the direction of wind blowing throughout our farm. Mostly the winds are coming from southeast from this direction, so that when the installing the equivalent flex tower, this direction was considered as a preliminary, so that farms which are located from this direction or carbon flux steam from this direction is going to be measured here through these are the name of the equivariance flux towers. Here I present only six, but totally we have 9 equivariance flux towers. So equivariance flux towers not measuring only greenhouse gas. These are also providing some very important biometrical variables. So that these are some of the biometrical variables measured by our equivariance flux towers, so that we can understand what is happening on the, for example, on evapotranspiration, on ecosystem respiration under different ecosystems, and seasonally what is happening, so that we can even use this biometrical data for other models, for example, in our envision in the future to more set up hydrological or set up ecosystem model. Some of these variables may be used as input for our models. This is the most beauty part of equivariance flux towers. We can measure the change in carbon flux, for example, even every minute, starting from half hour until hour. Here, I try to present only at hourly scale. So what's happening at hourly scale? The first thing is gross primary productivity. Gross primary productivity, it is very high. It is very high in July and at daytime. And this from 8 a.m. about 2 p.m., 4 p.m. high in this 10 p.m. to 1 p.m., maybe 12 p.m. Around that time, it is very high. The reason is there is high temperature in July, and there is more photosynthesis in July, more productivity in July, so that it is high in gross primary productivity. Just parallelly, carbon flux is high sink of carbon at the daytime, while there is high emission, not emission actually, a release of carbon, which was stored at the daytime, because at nighttime, low photosynthesis or almost no photosynthesis. Due to that, there will be an emission return of carbon from the systems like due to metabolic or ecosystem respirations happening. While in dry season, like for example here in January, it is low vegetation cover. Due to that, at that time, the sink of carbon capture is low, not compared to July, August. In these dry months and not cold months, the carbon sink is low, while high carbon sink we can have is in July, August, like that, even June. So a lot to say about this. First thing is we may need to increase more vegetation cover, more crops during July to increase our opportunity to sink more carbon in our farm. And another thing is it may be good to start about thinking to increase or to look for crops which are tolerant to cold weather. For example, if we have some cold weather crops in January, December, that may be another opportunity to increase carbon sink even in cold seasons like January. That was about at hourly scale. And we have seen what's happening at daily scale. And here is, you can see in the months like summer and spring, this is a way of sinking, high sink of carbon in these months. While in dry months, like January, December, there is lower sink of carbon. Even it looks like our farmers were source of emission rather than source of sink. One thing which get my attention is this: what was happening in this case. These two equivariance flux towers even though it was in summer, in August, July. These two covariance flux stars were source of carbon rather than being sink of carbon like other flux stars. So that we need to know how this is. And in these cases, we need to know about the history of our cropping season. So I have to remind and check out our cropping season. And in 2023, this season in 2023, the end of July and first week of August, this is the season we plant sorghum. So that in this period, like end of July and until August 8th, the farm was under plowing. We planted sorghum in August 8th, so that at that time the land was bare, no vegetation on the area where these two covariance flux stars were installed. So that you can see how our management, our activities are impacting the net change in carbon flux. Even though we are in summer, it is not only being summer or being in winter. We can have sink or emission of carbon. It's about our activities. So similar with that of the daily and hourly, we can see in these months there is high sink of carbon into through our vegetations, while in this January, February, and end of starting from November, like lower sink of carbon, even looks like emission of carbon is record measured by our covariance flux stars. So we have also tried to see what's happening related to not only carbon, what is happening about water flux, energy flux on our research farm, particularly on our pasture and crop agro-system, and which variable is following similar pattern of carbon or water or energy flux. Here we can see mostly it is evapotranspiration, which follow similar pattern with that of carbon flux. And GPP, of course, it should be identical to that of carbon flux, so that when there is high GPP, then there is more sink of carbon. And this is about energy flux and comparing with water and with carbon flux. So latent heat flux, of course, it should be similar with that of evapotranspiration. So latent heat flux is strongly correlated, but negative correlated with carbon flux. While it looks like sensible heat flux, it has no correlation or low correlation with other, for example, water flux and with carbon flux. So here is not only carbon, we are also working on soil moisture. So that first thing we try to understand is the soil moisture in summer, and it get increased in winter seasons. This is one, and there is similarity on this measurement from different sensors. Some of them are located on crop agro-system, and some are located on pasture agro-system. And one thing we add here is SMAP satellite product, and how it capture the soil moisture measured by our sensors. It looks like SMAP well agreed with soil moisture measured by sensors. And here is just one thing we need to improve is our spatial maps. So what is happening in each grid after we do something, after we apply any soil amendment or any nutrient application or any water experiment, and what to happen on each grid. So that is the case. And at this time, there were not more than 100 sensors were used to develop these grids. But if we use this season, we are going to have more than 500 sensors. This map will be more improved one, high quality soil moisture spatial maps we will have for this season than this season. So we may say low soil moisture sensor in summer season in December on pasture plots than the the crop seasons. So again, we need to see what was happening on our activities on farm. In December 2023, this the sorghum, the straw, we didn't harvest the straw. It was covered by the straw, the sorghum. So that may be the reason why there is significant high or better soil moisture on sorghum plots than pasture plots. So we have a lot of data, but still this much or huge potential of data and some revolution on the data analytics. These all are tempting even our objectives to reach out our farmers, to reach or increase our impact throughout other regions, throughout at least Texas. This all trigger us to have more work. So another data source we have to work is on machine learning. So that the first thing we need to do is which variables are important for our prediction. That is the first thing we have to see. Even we have removed some variables like ecosystem respiration, just to avoid some hegemonic effect of the variables. And still, it looks like some dominant effect of evapotranspiration and latent heat flux on carbon prediction, carbon flux prediction. Here again, we have we are more super effective in predicting carbon flux using machine learning techniques. But still, it is partly attributed to high or better quality of data we generated from in-situ sources, equivalent soil source and soil moisture sensors. So that this should be not the only or the maximum objective we have to when we apply machine learning techniques. Rather, we need to, there are areas, for example, if we want to know about machine learning equivalent flux stars, we don't have flux stars or moisture sensors throughout Texas. We have farmers with whom we already took agreement to implement some technology on their own farm. So we don't have flux stars there. For that, we need to look for other means of data. So that is, at least we need to improve our machine learning techniques by increasing our other data sources. We include here other data sources, remote sensing products. Still, the resolution is about 250 millimeter grid, but we consider these parameters in our machine learning environment. And you can see how these features, for example, leaf area index and fraction of radiation, which is active for photosynthesis, these are looks like important variables we need to consider in our machine learning techniques, so that it is just to see, for example, which variable is more important and less important. Like in this case, if we don't have data like related to soil heat flux, related to NDVI or related to wind speed, we may skip these variables and focus only on these most important variables. This is one method of testing the relative importance of features or variables we need to consider for our machine learning. Another method is Sharpe value. That is exactly the relative impact of each variable for our prediction. For example, here is the effect. For example, like if we consider latent heat flux or wind speed or leaf area index, they may contribute like a reduction of or sink of carbon by a ratio of 1.5 1 gram of carbon mole per meter square. But this effect may become more significant on pastoral growth systems. If we see these variables may trigger more change, more sink, and of course, due to the interactive or complex interaction between the variables through seasons. So this effect not only source of carbon, that may also result emission of carbon to the atmosphere. But at this stage, you can see these variables are more important at this Sharpe value. So using that, unlike that of the measurement we have at our farm at every 30 minutes, we have only at daily scale. So we consider here the data at daily scale, and the data from vegetation-related variables, leaf area index, NDVI, and fraction of vegetation, which is active for photosynthesis. Still, you can say these variables or our machine learning techniques are effective. And of course, that are not more effective as we did for at our research farm, so that we may scale up these machine learning techniques throughout the region, throughout the state, and we may still consider to use these techniques to reach or to monitor changes on like our farmers' farm after they apply different technologies, nutrients, and like that. So there it looks like more similarity in soil carbon, actual and predicted carbon flux after applying machine learning techniques. It looks like our machine learning techniques are effective in capturing the actual carbon flux measured by the equivariance flux styles. So if we are going to see change in carbon flux, and if we are going to apply machine learning throughout the state, we don't have equivariance flux styles. The other sources may be remote sensing data sets, so that we may use the remote sensing data sets, and we may initiate to improve the resolution of remote sensing data sets through applying these remote sensing productions, machine learning methods. So I have these conclusions from our global climate models, from our hydrological models. It is fair to say there is a change in historical and future climate change, a change in water quality, and we have seen upward and high elevation, upward movement of plant hardened zones, which will be opportunity or challenge for our growth. And integrating in situ measurement with remote sensing and machine learning techniques, we can say it's going to refine the accuracy and resolution. Of course, we need to see how the resolution will be improved after applying machine learning techniques. At least we can apply these techniques for carbon flux and soil moisture. So with change in environment, like climate change, there are different adaptation different approach, like adaptive scenario based optimal. We may have a good debate on that, but I believe we are working on look for optimal management technologies which can provide us better benefit in reducing climate change, in increasing agricultural productivity, and in sustaining our the health of our ecosystems. So these are my team. I'm very happy, and it is a great opportunity to thank. Some of them may be here, or some of them may be at the center or at one corner of the farm. I'm very, very grateful for the help I am getting from them. And of course, I'm also very thankful for you listening to my presentation. Thank you.
Great. We have opportunity to ask questions to Dr. Tafara. So if you have a question, please raise your hand and we'll give you the mic. Also, we encourage the online colleagues to also post their questions. We'll be happy to address your question as well. Any taker? Okay. Please pass it.
Good morning, everyone. Sorry I'm late, but wanted to start with a comment, and I'm so happy to see a room full of folks. So a couple of weeks ago, my leadership team, which we call the executive leadership team, the missionary leaders, the functional area leaders, consciously discussed a more intentional effort, not only for us to attend as leadership team, but to bring other folks. So in that spirit, I happened to run into Miss Alexis Agard, who works in the Office of International Programs, and brought her along to this. So I would encourage the rest of you to do the same. Bring somebody who's not aware of what we do to this land grant seminar series, because at the end of the day, land grants touch everything. But my question to you, Dr. Tefera, is fascinating presentation. Great to see the engaged team and so on. But in simple English, if you were explaining to a legislator what the significance of your findings is, including for the benefit of Ms. Alexis and myself, I'm an economist. I don't understand all this stuff in too much detail. But in simple terms, what is the significance of your research?
If I say, if I look only for the result from carbon flux, so I can say our decisions, our activities will have a direct effect on carbon flux. So it should be not only about carbon flux, but we have to say the ecosystem health, so that the change in carbon flux, better soil moisture means what to happen on agricultural productivity, so that we have to see our decisions, our active technologies, which can increase first the environment, like carbon flux and soil moisture. Then if we have better soil moisture retaining in the soil, so that which means there will be high agricultural productivity, so that at this stage you can say we can ensure both environmental objectives and agricultural objectives, which means, for example, more vegetation cover, which means high sink of carbon, but more vegetation cover, which is about also high production. Production may be related to grass or leaf hay production, it could be. So still, nature may challenge us. For example, in dry seasons, we may not increase more sink of carbon, but still we can see how we increase carbon or soil moisture in dry seasons. That is what I can say.
Okay, so it's good for the people, for the planet, and profitability.
Yes.
I have a question here.
Thank you, Tefera. It was wonderful and massive set of data. Very, very impressive. My question is, when you are taking the leaf area, the indices, did you look at the vegetation composition versus the monocultures, like you grow a crop that will become a monoculture, and comparing to the natural vegetations? And here we have a lot of deciduous plants. They shed the leaves during the fall time. So how do you refine those data?
The one I present about leaf area index, that has not, from that we can say nothing about the composition of plants. But if we are applying the leaf area index measurement on our farm, that can give us more detailed information about the composition, the canopy structure, and the change in the leaf area index through seasons. So this is the most sensitive product which I have presented. So from that, it's hardly possible to say about the composition of plants.
Okay, so my question has to do with soil types. I know our farm, we mostly have sandy loams soils, but based on what you have seen so far, what is your speculation on variation in soil type or soil texture on carbon flux?
So that's another good opportunity. So one of our source of measurement is soil carbon. So soil carbon is another measurement we are doing. So today what I present is the carbon flux from the equivalence flux stars from the system, which is about, for example, it is a measurement like about 2 meter height from the ground. So it is a lot to say, and based on the measurement from soil carbon flux rather than from these equivalence flux stars. So these equivalence flux stars can say nothing about the soil texture. Of course, we need to increase our spatial coverage to say the effect of soil texture on carbon flux. The soil texture in our form are mostly homogeneous, almost, I can say mainly clay. So I don't know what to happen if the texture is morely sandy or loomy texture. And we may have that type of presentation in the future. But for this presentation, I can say this soil texture is good and this soil texture is not good for carbon flux.
Yeah,
Dr.
we have a
Tefera,
question here.
Dr. Tefera, thank you for presenting us global, very comprehensive data, which are observatory type of science, where you kind of say, okay, what's out there? But to understand the sort of things that we can do better to improve the carbon capture in a global scale, there is a need for mechanistic experiments, like you manipulate the soil chemistry, you manipulate the vegetation types and all that. So based on the data that you so far have analyzed, what type of mechanistic experiments, like you do something, plant something, change the chemistry, and then you do all your measurements, what can be done to improve the carbon capture in the global scale? Because if you look at the world, including our country here, there are vast areas with no plants. But with the drones and everything these days, we can plant any kind of thing that is suitable there, including fruit trees, evergreens, and all that. So what are some of the ways that you can do manipulative experiments to understand this?
Okay, thank you. So what I can say here is mainly you have seen these are the vegetations which are important to sink carbon. I may say to increase carbon sink, we need to increase vegetation cover. But vegetations can be also source of carbon. So we have to work on that. For example, at our research farm, after we plant our experiment, for example, in dry season, like after our experiment, the straw is going to be a source of carbon. Otherwise, we have to put below the ground, or we have to use for other sources. For example, in our system, we are planning to use the straw, plant straw, as source of biochar, rather than living on open space. So at least we have to, as far as my knowledge, it is good to move forward about working on crops, vegetations, particularly during dry seasons. At dry seasons, we have to work more on reducing emissions after a dry mass of crops, even after the trees are getting dry. Another source, after trees are getting dry, another challenge is there could happen wildfires, for example, that trigger much more emission of carbon. So that I think we need to move forward on the working on managing the dry seasons. Dry seasons, we don't have more green plants, but we have to manage the dry part of vegetations.
Well, we have a question here. It says, how does the interplay between solar radiation, evapotranspiration, and plant physiology in the east and west facing plots shade long-term carbon sequestration pattern? And could these microclimate differences influence broader climate resiliency strategy? So if you have a west-facing versus east-facing, what's the implication of that on carbon sequestration? Okay. So although the person who asked the question is here, but he typed it, which has helped me read it. So
yeah, okay. So the main thing is when we put our equivalent flux cells, we didn't consider putting in either direction. The main thing is the preliminary data was considered where to put the equivalent flux cells, so that the equivalent flux cells are installed in a direction where it captures wind coming from southeast, so that if we put our equivalent flux source from other direction, it may have another result in narrow circumstance, because we have seen wind is coming from west part is really happening. So that may have another implication on the result. On micro scale, we have to increase our spatial coverage of our experiment to see the impact at global or broader scale. Otherwise, and it's our objective is not only experimenting out our research farm. It is about to increase the coverage, our outreach to the farmers. That is the way we can bring change, more broader impact on the broader impact of these technologies on the global climate.
Thank you. And we have another question here.
All right. Thank you very much, Dr. Tafarra, for very impressive presentation. My question is two. One is, in case, after all this data, in case if you have developed a model, I mean, it's a kind of mathematical model or allometric model, so as to measure this soil moisture content, carbon content. For example, in case if I miss, for example, in case if I don't have this machine, and if I want to take or at least estimate the emission rate. So have you so far have developed mathematical model or any kind of model? And another question is, so you have actually assessed a lot about Texas climate, which is very good. But have you had an opportunity to compare carbon sequestration potentials of vegetation, probably compared to some other states? Because I believe most of at least the area where I am around is mostly grassland. I don't think it is more of a big trees. Of course, we have a big trees, but I have still an issue with the anatomy of the vegetations. So have you had an assessment about that? Thank you.
Okay, thank you. So to start from the first one, we don't have empirical or mathematical model so far, but it is our objective is to go for that ecosystem models. That is the only way to increase our effect to broader spatial scale. So far we don't have, but that is our objective. So remember the machine learning, remote sensing, that all are about circulating, looking for other ways of understanding carbon flux at broader scale. Second one is we don't have other measurement, other areas. For example, we don't have equivalence flux source in other areas. We don't have soil carbon measurement on other areas. So far, we have only at our research farm. So last week, for example, we had a contract with farmers. So from that, they are going to apply some technologies. So our term is we need to go there and measure carbon, soil moisture from their cropland, from their pasture, from their even I think that some of them have forest. So that is the way we will have measurement from other areas. Another thing is, so we have here the carbon measurement, soil moisture measurement, and we'll have other measurement, for example, this season. Then that will be another opportunity to look for other data analytic works. So our work here is not only about experiment, about measuring data and about identifying which measurement is good and which measurement is not good. Rather, we will increase our effect toward broader scale.
Okay, we'll leave the last question for the best. So one of our graduate students is going to ask you a question here.
Thank you, Dr. Tefera. Lovely presentation. I enjoyed it very well. But my question is in regards to one of your slides where you said the changes in plant hardiness zones. So my question is, by the shift in 2099, how will this affect plant competition, species migration, and land use in Texas, Oklahoma, and Colorado? And what are some of the strategies you suggest towards preventing all of this from happening when I'm looking at this chart here that you have?
So the first strategy is there should be a substantial, sustainable reduction in emission of our greenhouse gas. That is a way to reduce increase of temperature. Otherwise, an increase in temperature will continue. Other strategy, if we continue emitting carbon, our farmers, our growers may challenge or may withstand this challenge, maybe through genetic engineering, like improving the genetic part, which identify trees, fruit trees, which can withstand high temperature. Otherwise, even the lower part, for example, southern part of Texas, there will be more temperature. So that will be challenging for the existing crops. Still, we may need to improve maybe the genetic or variety, crop variety, tree varieties. That may be my suggestion.
Thank you. Let's give him another. Thank you, Dr. Farah. Thank you for the question.